everyone, it's Mrs. Jennison here and I'm an Associate Director for Outward Grange Academy's Trust. Welcome to our lesson, and today we will be learning about bond energy calculations. This content is higher tier only. Please make sure that you have a pen and a piece of paper with you so that you can work through the activities in the video with us. For today, it would also be really useful if you had a calculator. Our challenge for today is to be able to explain whether a reaction is endothermic or exothermic in terms of bond energies. Our aspire is to be able to calculate, using bond energies, the energy changes in a reaction. Now, as I've already said, this is higher tier content. So, what happens to the bonds when substances react? Now, you may be familiar with this reaction. Methane will react with oxygen in a combustion reaction to produce carbon dioxide and water. And you can see the molecules of methane, oxygen, carbon dioxide and water on the screen. For those reactants to form those products, all of the bonds of those reactants must be broken before they can form the bonds of the products. So during that reaction, there is an overall energy change. That is due to energy needing to be supplied to break those bonds of the reactants, and energy is then released during the bond formation of the products. Whether a reaction is endothermic or exothermic it'll all be dependent on, did it take more energy to break the bonds, or was more energy released during bond formation? So, remember, the overall energy for reaction is dependent on two things: the bonds that are broken, which takes in energy, and the bonds that are being formed, which releases energy. Now, you may remember these diagrams from a previous topic. In an exothermic reaction, the energy released making the new bonds is greater than the energy that was taken in breaking the bonds, which means overall there is a temperature increase seen as energy is being released to the surroundings. Now, that is why on our energy profile diagram, the products are at a lower energy level than the reactants because energy is being lost overall to those surroundings. In an endothermic reaction, the energy that is being taken in breaking the bonds is greater than the energy released in making the bonds, which means overall there is a temperature decrease seen as energy is being taken in from the surroundings. Now, I'm just going to give you a little bit of time to answer some quick questions based on what I've covered so far. Okay, so chemical bonds during a reaction, the reactant bonds are broken and the product bonds are formed. The energy profile for an exothermic reaction, I've just placed that on the screen. Remember, when you are labelling things like the activation energy, you've got to label the height of the hump, not just the hump. And the energy released is the difference in level between the reactants and products. Breaking bonds takes in energy and bond formation releases energy. And in an endothermic reaction, more energy is taken in breaking bonds than is released in making bonds. Okay, so if we know the energies of the bonds involved, we can actually calculate the energy change. So an example I'm going to use is actually the chemical reaction in hydrogen fuel cells. So hydrogen reacts with oxygen to form water. Now, I'm just going to put the molecules on the screen. Now, quite often in an exam, you'll be given a diagram of the molecules, but you may not be given the number of them. So as you can see, I've actually put physically 2 hydrogens in there. And then we've got an oxygen molecule, and then I've got 2 water molecules. Now that means in those 2 water molecules, I have 4 oxygen to hydrogen bonds, because there's 2 in each molecule. Now remember, in this reaction, all of those bonds need breaking before they can form the products. Okay, so we can't be skipping out any bonds. What I've done is I'm actually going to walk you through the first one, and I've recorded it to insert into this video. I'm going to add a video here that works through how to make one of these calculations. Then I'm going to give you plenty of opportunities to practice this yourself. And so I'm just going to work through this first example with you. Now, we're just going to take the reaction where hydrogen, 2 molecules of hydrogen react with oxygen and form 2 molecules of water. Now, I have been given them here in the question, but I am actually going to write it out myself with the molecules. So I've got 2 of this molecule reacts with 1 of this molecule to form 2 of this molecule. Now, the information I've been given in the table is that it's the amount of kilojoules required to either break or make each bond. So that means this hydrogen bond requires 436 kilojoules to break it. And I have 2 of that bond. This oxygen to oxygen bond requires 498 kilojoules to break it or make it. In this case, it's break because I've got my reactants. And this bond here, O to H, requires 464. But I've got 2 of them in this molecule. And I have 2 of that molecule. So if I look at my reactants first, I've got 2 of that hydrogen to hydrogen bond and 1 oxygen-oxygen bond to break. Now that will take 436 times 2, add 498, 1,370 kilojoules per mole. Now I'm going to form these bonds, and forming bonds releases energy. And I've got 2 bonds in the molecule, and I've got 2 of that molecule. So 464, add 464 times by 2 is 1856. Okay, now the overall energy change or enthalpy change, delta H, is the reactants minus the product. kilojoules. So it's the energy taken in breaking the bonds of the reactants minus the energy that is released forming the products. Now think about that. That energy is released. That's why it's negative. It is lost to the surroundings. It goes out of the reaction. So 1,370 minus 1,856 gives us a delta H energy change of minus 486 kilojoules per mole. So now you've seen one example, it's time for you to have a go at one of these calculations for yourself. Another type of fuel uses methanol instead of hydrogen. And you can see here that the diagram represents the reaction inside of that fuel cell. So we've got methanol reacting with oxygen to form carbon dioxide and water. And you've got the bond energies listed on the screen also. I'd like you to calculate the overall energy change for that reaction. So instead of just adding a mark scheme on this slide, I'm going to play a video of me working through this calculation for you, so you can use that to help you mark your answer. Okay, so if we look at the reactants first, I've got, in this molecule of methanol, I've got 3 carbon to hydrogen bonds, but I've got 2 of this molecule, which means I'll have 6 carbon to hydrogen bonds overall. I'm also going to have carbon to oxygen and 2 carbon to oxygens, because there's 2 of the molecule, and 2 oxygen to hydrogen bonds. My other reactant is oxygens. That means I've got 3 oxygen to oxygen bonds. So let's work out the energy required to break the bonds of the reactants. So I'm going to replace all of these numbers in. So I've got 6 times 412. Add 2 times 360. Add 2 times 464. Add 3 times 498. which gives me the energy required to break the bonds of the reactants as 5,614 kilojoules per mole. Right, let's do the products now. So on the product side, I've got 2 of this carbon dioxide molecule, and the molecule has 2 carbon to oxygen bonds. So that means I've got 4 carbon to oxygen bonds added to the 2 hydrogen to oxygen bonds, but there's 4 of that molecule, so there's 8 hydrogen to oxygen bonds. So 4 times 805, add 8 times 464, which equals 6,932. So now, if I want the overall energy change, it's reactants, the energy required to break the bonds of the reactants minus the energy released making the bonds of the products, which comes out at minus 1,318 kilojoules per mole. Okay, time to have another one. So another practice. This equation shows the reaction of methane with oxygen. So you've got the equation on the screen and all of the bond energies. I'd like you to calculate the energy change for the combustion of 1 mole of methane. Okay, so I'm going to insert the worked example here for you to check your answers as we go through. We're calculating the overall energy change for the combustion of 1 mole of methane. So we have our methane molecule, which is essentially 4 carbon to hydrogen bonds, plus 2 oxygen to oxygen bonds. So these are what I'm breaking, and that forms 2 carbon to oxygen bonds and 1, 2 times 2, so 4 hydrogen to oxygen bonds. So these are what I am forming. So this is where the energy is going to be taken in, and this is the energy that's going to be released. So if we use the numbers from the table, that's 4 times 412 added to 2 times 496, which means my reactants require 2,640 kilojoules per mole to break. And when I form my products, I will release 2 times 803, add 4 times 463. So 2 times 803, add 4 times 463. I release 3,458 kilojoules per mole. So the overall energy change is reactants minus the products, which means it will be minus 818 kilojoules per mole. So last practice one, and then you're going to have a go at an exam question. So the equation for the reaction can be represented as ethene reacting with bromine to make bromoethane. Okay, the bond energies are on the side. I'm going to give you a little bit of time to have a go at this one. Okay, again, I'm just going to insert a worked example for that calculation here for you to check your answer with. First, I'm going to list all of the bonds in my reactant. So as you can see, I've got C to H, and I've got 4 of those, and a C double bond C. I've also got a Br to Br bond. On this side, I've got 4 C to H bonds, 1 C carbon-carbon bond, and then I've got 2 carbon to bromine bonds. So what I'm going to do now is I'm going to add in my bond energy. Now I'm going to work out my reactants first. So 4 times 413, 614, add 193. So 4 times 413, add 614, add 193 is 2,459. So that's the energy that will be taken in breaking my reactants. Now on this side, I've got 4 times 413 again. Add my carbon-carbon, which is 348. Add my 2 carbon bromines. So 2 times 276. And I will get 2,552. So my overall energy change is reactants minus products, which means delta H will be 2459 minus, which is minus 93 kilojoules per mole. Let's move that up so you can see that last step. There you go. So now that we've had a go at a few of these, it's time to have a look at a final example from an exam. So the chemical equation for the combustion of ethanol is ethanol plus oxygen forms carbon dioxide and water. They've given you the display formula of these molecules here, and they'd like you to use the bond energies to calculate the overall energy change for this reaction. Okay, so the reaction is exothermic. Explain why in terms of bonds broken and bonds formed. Then complete the energy level diagram for the combustion of ethanol. On the completed diagram, label the activation energy and the overall energy change. Okay, so the mark scheme for those questions is on the screen. The overall energy change for the initial reaction was 1,276 kilojoules per mole. If you had that number, you would get all 3 marks. But if you didn't, check your working. So the energy change for the reactants was 4,722. So that's the energy taken in breaking the bonds of the reactants. And for the products, the energy released was 5,998. Now, if you got one of those wrong, you'd get the mark for the correct side, and then you'd get a mark for substituting energy values. The next part, it's exothermic because the energy released when bonds form is greater than the energy used when bonds are broken. And that statement will be for 2 marks. If you only said energy is released when bonds form, you would get 1 mark. Then your diagram should have the products line lower than the reactants with the hump for the activation energy labelled and the overall energy change labelled. That's everything for me in this video, and I will see you soon. Bye.